The second part of updating the tri-state fertilizer recommendations is going to be focusing on crop response to P&K fertilizer. So, what's the evidence that we have for when we actually need to apply, and at what rates, et cetera, et cetera. So, I got here, and you'll take a look at this tri-state fertilizer PDF document. It's posted online, in Carmen. But the reality is that there's not a whole lot of data that goes into it, and I was very curious to know, after hearing so many reports of it's too low or it's too high or it's just right, trying to understand what some of the data were behind the actual recommendations themselves. Okay. So from 1976 to 1999, there was a soil fertility specialist here named Jay Johnson. And when I showed up to my job about 6 years ago, there was a stack of these soil fertility reports in my office that had just been passed down. Okay, there was a gentleman, Robert Mullen, a great scientist, that was here for about 6 or 7 years, and then he moved on to a new position. But this was really kind of the heart and soul in terms of what the tri-states, at least the Ohio piece, was built on. And we went through and we painstakingly digitized all of this information. We extracted data from PDFs into Excel, and we essentially analyzed any phosphorus or any potassium trial that was conducted at Ohio State over this 25-year time period. Okay, here are the different counties where the trials were conducted. You can see the vast majority of counties are in Clark County, or vast majority of trials for P&K were in Clark County at the Western Branch. There was the second most were in Worcester, and then at the Worcester campus, and then about 15 or so in Wood County at the Northwest Ag Research Station. So really the three agronomy farms at our Ohio State University farms represented the vast majority of this information. Okay, and so again, this idea of relative yield, if we want to develop critical levels and figure out crop response, we need to calculate this relative yield. So we've seen this before, but let's just talk a little bit more about this. So imagine, and this is like appropriate for large strip trials that were conducted across the state that we'll talk about here in a bit. Imagine we've got a row of crop. We are going to treat one section or one strip as unfertilized, where we're not going to apply, say phosphorus fertilizer, and then we are going to apply phosphorus fertilizer to a second strip. We do this, of course, randomized and replicated, so we don't do this just one time on a field, but we have multiple strips of each one across the field. We calculate the relative yield as the ratio between the unfertilized divided by the fertilized times 100. So in this case, if it's a soybean field, the unfertilized yields 45 bushel, but the fertilized yields 50 bushel. We do the math and we get essentially a 90% relative yield. That's a 10% reduction in yield that we, for better or for worse, attribute to phosphorus fertilizer because everything else was treated exactly the same. Now, if it's just two strips, it's a little suspect, but when we have multiple strips and they're randomized, then it becomes a lot more powerful information. Okay, so this is the basis that we develop these recommendations on. So getting back to that old Jay Johnson data from those fertility reports, we reconstructed these relative yield graphs. Okay, and so this should look familiar from last lecture, where we've got relative yield versus soil test phosphorus and relative yield versus soil test potassium. So these are the potassium trials and these are the phosphorus trials. And these dashed red lines are the critical levels that the tri-state outlines. In other words, If you're below this dashed line, then you are deficient. If you're above it, you're sufficient in the maintenance range. So we strive to build our soil test above 15 Bray phosphorus and typically 100 ammonium acetate potassium. Each one, now it's important to note that each one of these dots represents a trial that has multiple replications. Again, so thinking about that calculation, we take fertilized divided by the fertilized. So what we typically do when they're replicated, we take the average yield of the fertilized, the average yield of the unfertilized, and we multiply that by 100. So we have a much greater chance of just much more statistical power for this, okay? It's important to note, too, that we've got non-responsive, i.e. not statistically significant, the black dots, and then the gray dots are statistically significant. And so what this means is that when we're below the critical level, there are some trials that were responsive to fertilizer, but there was plenty of trials up here that were not. And so it's important to note that just because you're below the critical level doesn't mean you're guaranteed a yield response, okay? These data are reported in this fact sheet if you want to dig deeper. But it was actually coming into this, I was quite shocked how clean the relationship was. Really, out of all these trials, I think 92 for potassium, there was really just one that was above this critical level and was responsive to potassium. So very small odds in that regard. Okay, so basically one out of almost 1% chance. Okay, so that's what happened to go into the recommendation. So what about more recent work? And so I'm going to talk about two pieces now, and I'll try not to yap on and on, but I'm going to talk about two pieces I think are very important in terms of framing our new recommendations. Okay, so the first piece I'm going to talk about are these long-term P and K plots that Robert Mullen started in 2006. There's three counties here, 3 rates of P fertilizer, 3 rates of 3 rates of potassium fertilizer, and then typically a corn soybean rotation. The earlier part of this experiment had a couple different rotations, but it was either corn soybean or it was corn soybean. So we've looked at that rotation effect. There was no difference, so we've combined the data to present here. Okay. We'll start with soil test phosphorus over time. So here's our 3 sites. Northwest, that's Wood County, Western Clark County, and then the Worcester site in Northeast Ohio. Malic 3 phosphorus. We started here in 2006. These dashed lines are essentially a new critical level of 20 to 40 part per million. Okay, so this is the range where we want these soils to be. And we can see soils were sampled here in this first year right after an initial soil sampling, as well as in Worcester. We have 3 rates of potassium fertilizer. We have a 0, which actually represents a set of plots replicated 4 times that were cropped annually every year and no fertilizer was applied. We have a 1X, which is essentially fertilizer that was applied at maintenance or at crop removal. And then we have a 2X, which is double crop removal. And then when we hit these arrows in 2016, it turned into 3 times crop removal rate. Okay, so we can see from this that Northwest has a lot of variability. We don't entirely understand what's going on there. But for the other 2 sites, and for Northwest as well, not fertilizing with P, we see kind of these drop-offs that happen and then essentially a plateauing. But fertilizing at crop removal typically keeps soil test level maintained at its current state. And then when we apply 2 or 3X, we're building that soil test level up. So that makes sense, okay? And it's just good to kind of see these data over, it's a unique data set because people don't do this in the real world, right? This is research farm when you're going to be soil sampling every single year, and then have these, multiple different types of P, different types of K fertilizer treatments. Okay, so for soil test P, we're pretty comfortable with where this is at, and it makes sense. But for potassium, it's a little bit of a different story. Okay, so potassium, we started elevated at Northwest, but the other sites started in kind of a reasonable maintenance range from 100 to 150 Malic potassium part per million. Again, year on our x-axis, and we can see that, at the western site, we have a drawdown of the unfertilized, and at the Worcester site, actually all the sites. But what's kind of disturbing, or what's unfortunate, or makes us scratch our head, is that this at removal rate, 1x, is reduced across the board. So over this same time point, we go, when we're applying at crop removal, we're seeing a general reduction in across all three sites. When we apply 2 or 3x, that's really, depending on where you're at, it's basically just maybe maintaining, but maybe building a teeny bit, but not too much. So the tri-states, if you dig into them, recognize that K is harder to maintain than phosphorus. That potassium, soil test potassium, is harder to maintain. So they say crop removal plus an additional 20 pounds. Okay, that's kind of the recommended rate. Here we can see that we probably likely need more than that if we really want to maintain soil test levels. So we don't have really good information about this, but we're going to continue this experiment and try to figure out a little bit more reasonable level for the maintenance of these soil test potassium levels. Okay, so this is just the soil dynamics, right? But are we really fertilizing to maintain soil levels, or are we fertilizing for the plants themselves? And we would argue for the plants. We can look at drawdown ranges for soil test P. This is where we started. This is where we ended. Somewhere between 1 to 2 part per million per year. For potassium, again, where we started, where we ended after those 13 years. Around 5 to 7.5 part per million decrease per year. Okay, but let's look at yield data. Yield data tell the story in terms of if the plant needed it. So we might be trying to manage soil test levels, but what is the plant responding to that? Okay, and so this is phosphorus. We've got our 3 sites: Northwest, Western, and Worcester. Corn on the top row, and then soybean on the bottom row. Okay. Our fertilizer rates are the same as 0, 1x, and 2x. So again, we look at yields of crops that literally have not been fertilized, or plots that have not been fertilized for many, many years. Okay. These red dashed lines represent where, at what point that site went below critical level, and so we would expect crop response to phosphorus be a lot higher. Okay, and what we can see here is that soybean is typically not very responsive to phosphorus. There are years in corn where we do see responses, and we can see some general trends of these red or unfertilized plots being a little bit less than the fertilized. Okay. Now let's look at potassium. Potassium Northwest, there was essentially, because it was elevated levels, no response potassium over those 13 years. The western branch, particularly with soybeans, we see the biggest evidence of yield reductions without fertilizer. So at this western site, soybeans need potassium, and when we get below critical level, we can see kind of consistent trend. Not all years. Here's a year where that didn't happen, but a lot of years where it's it's a believable trend. Worcester, not so much. Okay, So we can take all these data and kind of quantify them. And we can run statistics to say, it's nice to look at this to see overall trends, but at some point we should run statistics and see, do we have a statistically significant increase or not? And that's the gold measure for science, of course. So we had 108 observations in corn. There are 108 trials across those 3 sites in 13 years that said, compared a fertilized crop to a non-fertilized crop. 108 in corn and 90 in soybean. Of that 108 observations, applying phosphorus increased corn yields 22 times, actually we saw a significant decrease in corn yields 3 times. Soybeans 7 and 5, and for K, 8 times we got an increase in corn, 2 decreases, 15 increases and 4 decreases. Okay, so this really kind of plays into some old adage that corn is typically more responsive to phosphorus and soybeans typically more responsive to potassium. Now, interestingly, you take this and you divide it up based on soil test level. So again, when we're below the critical level, we believe that we have a much greater chance of seeing a response. When we're above the critical level, we have a much lesser chance. And so that's what these values in parentheses indicate. Of these 22 observations, 22 increases in corn yield, 16 of them were when the critical level was below, the soil test level was below that critical level. 6 of them when it was above. So again, the critical level is not some magical thing, but if we look at this and see the increases typically happen when the soil test level was below 16 and 6 and 4 and 3. And the same is true for K, 7 and 1 and 12 and 3. So when we're below that critical level, we have a much better chance of seeing a yield response. Okay, so now I'm going to shift gears and I'm going to talk about our on-farm strip trials. And I'm going to summarize some of that previous data here in a bit, but I want to talk a little bit about some of these on-farm strip trials. We ran these for 5 years across the state, okay? This was a major effort. We had looking at corn, soybean, and wheat, looking at nitrogen, phosphorus, potassium, and sulfur. I'm only going to talk about P and K here. We tried to cast a very broad net, getting a lot of soil diversity, a lot of different soil types and regions. We worked directly with growers. We worked with crop consultants or county educators, agronomists. We spent a lot of time trying to reach out to people and to industry contacts and say, we want to run strip trials. Do you want to help us do this? We essentially paid county educators, we paid private crop consultants and farmers small amounts to help offset, incentivize this for their time. But we let the farmers choose, have a lot of flexibility. Tell us what crop you want to grow, what nutrient do you want to look at, and then figure out your system. Okay, so all trials were replicated and randomized, and typically for P and K entailed a fertilizer or a fertilized treatment versus a check or a non-fertilized treatment. We sampled soil. We took plant tissue, reproductive tissue. We measured grain yields and took grain nutrient concentration. And then we had the growers fill out a management survey that tracked previous history and how they kind of managed for that growing season. So we have that information, okay? This was a major effort. It's very expensive to do this. It's not done very commonly. So we're fortunate to have a lot of industry support. Most of this project was funded by checkoff dollars, the Ohio Soybean Council and Ohio Corn and Wheat. So we would consider this basically an industry-led initiative that was facilitated, through Ohio State, and OSU Extension county educators had a lot to do with this. They did the lion's share of the work. Okay, so there's a lot of data here. I'm not going to get into too much of the nitty gritty. But for phosphorus, we had 102 trials over 5 years. 54 of these trials were in corn and 48 were in soybean. Okay, these are our soil test levels, and this is essentially just these are little violin plots, but it's a distribution, a frequency of corn and soybean versus the soil test level. So we can see that even though we begged and begged for farmers to come forward with fields that were in the maintenance range, the majority of them were in maintenance or above maintenance. So very few observations were actually below this critical level. This is the critical level here, and this is the maintenance limit. So this right here, in between this, is our maintenance range. Okay. Over 5 years, we had some very good corn yields, 192 bushel. That's well over statewide average. 62 bushels to almost 300 bushel was our average, etc. Okay, so let's move on and talk about some of the things that we found for these corn trials. Okay, so we found, on average, applying phosphorus fertilizer gave us a 3.6 bushel increase. But it ranged from minus 20 bushels to plus 22. Okay, the average relative yield was 89%, and that means essentially a 2% reduction when we did not apply phosphorus fertilizer. Soybeans, out of 48 trials, there was a 1.3 bushel increase. That, of course, ranged from negative to positive. Again, about a 2% increase across all trials. Now, all trials is, averaging this across all trials is helpful, but we have to understand that each one of these trials has a unique story, and should be kind of explored, but we don't have, of course, the time to get into that right now. Okay. Briefly, with potassium, we had 81 on-farm trials. Here's our distribution of soil test K. So again, more observations that were below the critical level, but most of them are in the maintenance range or above. So again, soils that have not been kind of drawn down or neglected but are fertilized well. I should stop here and say that this shouldn't be misconstrued to assume that all soils are high soil test, right? Like for P and K. This is just for the farmers that stepped forward and said they want to work with us. This is the fields that this represented. Okay, so that's an important distinction. Okay, so for corn, we had 33 trials for potassium. Fertilizing potassium increased corn on average across these 33 trials about 4 bushel, but it went from minus 45 to almost 60 bushel increase. Again, overall trials, that was only a 2% decrease when we did not fertilize. For soybeans, applying potassium fertilizer decreased, on average, soybean yields 0.6 bushels. So that means that when we fertilized, on average, we got a decrease across all these trials, a half bushel decrease. Okay, so it's clearly not a guarantee in terms of finding when we fertilize, we many times do not see yield responses, and this is particularly true when the majority of the sites, the majority of the soils are either where we would recommend or above where we would recommend. Okay, so I'm going to show you these Kate Nelson analysis. Okay, and this is again a statistical method for finding a critical level, and I'm not going to get into this, but it's the same kind of concept that we talked about with the relative yield, and then at some point we're decreasing. Okay, now this is I'm just showing you this. It's a messy data set, right? This is our on-station trials, okay, and this is across many years, 13 years all compiled together. And when we do this, the Kate-Nelson analysis tries to minimize the points, the observations in this quadrant and this quadrant, these open circles, and maximize the ones that are in this quadrant and that quadrant. That's what this Kate-Nelson analysis does. Very straightforward in terms of what it does. And this is often what we can do to kind of determine these critical levels. Okay, so for corn, for the on station, we see it's 22 part per million and 12 part per million for phosphorus. This is malic 3 phosphorus. And then when we go to these on-farm strip trials, okay, we find critical level of 26 for corn and 18 for potassium. And we did this for, I just said 26 for corn and 18 for soybeans. So this is both of these graphs you just saw for phosphorus. We did this for, split this out a lot of different ways, and I'll just show you this, for your own interest. But basically, we kept zoning in around a number around 20, which would be consistent with what the old recommendations were. 15 Bray part per million is about 20 Malic part per million. So again, not perfect. It's not an exact number, but it's what we believe is a good value, a good ballpark value. For potassium, again, around 100 or maybe a little bit less, but we believe that 100 is a good range to keep things within. Okay, so that was a big whirlwind tour, and I'm sorry. I recognize that I just dumped a lot on you. You're going to be responsible for kind of major. Not any of the detail per se, but more the kind of the major concepts here and understanding this. And for people that really want to do a deep dive, there's of course a lot more information here. But I think it's important to kind of, or at least maybe a little insightful or enlightening, to go through this process and see how some of this work has developed and what it kind of think through what it takes to actually develop these recommendations. Okay, so we spent a lot of time on this. And it's been a tremendous effort, and we're really very close to wrapping things up and releasing new recommendations. Okay, to summarize, our soil test trends, STP showed meaningful and expected trends in both building up and drawing down soil test levels. Soil test potassium, STK, failed to substantially build. So this is a little bit disturbing, especially when we think about recommending, if you're below that critical level, to keep applying potassium to build it up. Okay, we're having a hard time doing that, even with twice the removal rate, 3 times the removal rate. Okay. Grain yield increases to P and K were not consistent and suggest that soil has the capacity to supply P and K for many years without fertilization. This, I believe, folks, is a very important point. Looking at that long-term data set from the 3 farms that I showed you at first, those soils, when they're in the maintenance range, they are able to supply sufficient P and K for many years. There's this perception, I think it's part marketing that's out there, that crops need to be spoon-fed. If you're not fertilizing every year, if you're not, blah, 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 then you're going to have problems. And we just don't have any evidence to suggest this. So, it verifies or confirms in many ways this idea: if you build soil test levels up and keep them not a saturated state, but in a fertile state, that soil is going to be able to supply for many years. Okay. So our Kate-Nelson shows that really our critical levels, around 20 part per million of Malic 3 phosphorus, seems to converge with a number of different data sets and different crops. A critical level for around 100 for Malic 3 potassium is a reasonable approximator. It's not perfect, but it seems like as good a number as any to go with. The reality is that there's really no evidence that our critical levels are too low and that they need to increase. Okay, so that's a lot of the data in terms of picking our soil test levels and our critical levels. We're going to end this with a third part talking about actually how to develop those recommendations.